In the last lecture we learned how to add two matrices of the same size and how to multiply a matrix by a scalar. What we didn't do was learn how to multiply two matrices, for the reason that it's a little bit complicated. In fact, what we're going to do in the next two lectures is to define a way to multiply some, not all, matrices together, and we'll talk a little bit about why the definition looks like it does. The way we're going to define matrix multiplication is to build up from simpler cases to the most general case. And here is the simplest definition of matrix multiplication, which is that we define a way to multiply a row vector by a column vector. So let's suppose we have a row vector R, which has width n, and a column vector C, which has the height n. So those two n's really must be the same. We must have a row vector whose width is the same as the height of the column vector. We then define the matrix product R times C to be the number which you get by multiplying corresponding entries of these two vectors and adding them up. So R1 times C1 plus R2 times C2 plus R3 times C3, and so on. In symbols, that is the sum from I equals 1 to n of R sub I times C sub I, where R sub I is the ith entry in the row vector R, and C sub I is the ith entry in the column vector C. If you've seen dot products before, then this is like a dot product. So as an example, here we have a width 3 row vector. Here we have a height 3 column vector. Because the width is the same as the height, we're able to multiply them together. And the result of multiplying them will be 1 times 4 plus 2 times 5 plus 3 times 6. So that's 32 if you work this out. Okay, that's a special case then of our definition of matrix multiplication. The next most complicated situation where we're going to multiply matrices is matrix times a column vector. So again, we only do this in certain circumstances. So we will take a m by n matrix whose ij entry is little a subscript ij, and we'll give names to its rows. So we'll call the first row bold R1, the second row bold R2, and so on. That means that bold Ri, the ith row, is the row vector whose entries will be ai1 across to ain. Now let C be a column vector which has height n. So the height of the column vector is the same as the number of columns in your matrix A, which means that the width of these rows in the matrix A are the same as the height of the columns, or the height of the column vector C. If that's the case, then we know how to multiply rows in A into this column C, because we saw that on the previous slide. So we define the matrix product AC to be the height m column vector whose first entry is the first row of A times C, whose next entry is the second row of A times C, and so on up to its mth entry being the mth row of A times the column C. Alright, that's a little bit tricky to understand in the abstract, but it's much simpler if we just look at an example. So let's take the example when A is the matrix with 2 rows and 2 columns whose entries are 1, 2, 3 and 4. So in that case, A has 2 rows. R1 is the row vector 1, 2, and R2 is the second row here. That's the width 2 row vector whose entries are 3 and 4. Now let's pick our column vector C to be the height 2 column vector 5, 6. And now we notice that the height of this column vector C is the same as the number of columns in our matrix A, which means that it's okay for us to multiply A into C. So again, let me emphasize, we only define the product of an m by n matrix and a height n column vector C. So that means the number of columns in the matrix must be the same as the number of rows in the column vector. Okay, returning to our example, A times C by definition is the height 2 column vector whose first entry is obtained by multiplying the first row of A into C according to the recipe we met on the last slide, and whose second entry is obtained by multiplying the second row of A into C. So if we just do this, we're looking at the first row. That's obtained by multiplying the first row of A, which is 1, 2, which you'll see here, into the column vector C. So we get 1 times 5 plus 2 times 6, which is 17. And to work out the second entry of A times C, we multiply the second row of A, which was 3, 4, into the column vector C. So we get 3 times 5 plus 4 times 6, which is 39 there. So our matrix A multiplied into the column vector C gives us the height 2 column vector, whose entries here are 17 and 39. Let's do another example of this just to make sure we have the definition right. So this time we will take A to be the 3 by 2 matrix whose entries are 1, 2, 3, 4, 5, 6. And we will take C to be the height 2 column vector 7, 8. This time we're multiplying a 3 by 2 matrix into a 2 by 1 column vector. It's okay to do this because the number of columns of A is the same as the number of rows of C. They both have, well, A has 2 columns, C has 2 rows, so it means we're able to multiply those things using our definition. And the answer will have the same number of rows as A did. So the answer will be a 3 by 1 column vector. And the way we'll find that 3 by 1 column vector A times C is by multiplying the first row of A into C, and then multiplying the second row of A into C, and then the third row of A into C. So if we do that, the first row of the matrix product AC is obtained by multiplying the first row of A into C. So we get 1 times 7 plus 2 times 8, which is that first row here. The next row of A times C is obtained by multiplying the second row of A into C, so we get 3 times 7 plus 4 times 8, and that's the second row here. And finally, if we want to look at the third entry of A times C, then we multiply the third row of A into C, so we get 5 times 7 plus 6 times 8. That's too big for me to do in my head, but you get 5 times 7 plus 6 times 8 as the answer. Okay, I wanted to do this example specifically to point out that the size of A times C is not always the same as the size of C. In fact, the size of A times C is that it is a column vector, and the number of rows in the column vector, so the height of the column vector, is the same as the number of rows in the matrix A you started off with. Right, we're now ready to give our most general definition of matrix multiplication. So we take a matrix A, which is M by N, and we take a matrix B, which is N by P. That means the number of columns of A is the same as the number of rows of B. In this case, if we fix some notation, so we'll say that the columns of B are C1, C2 up to CP, and then we define the matrix product A times B to be the M by P matrix, whose columns are A times C1, A times C2, up to A times CP. Let's think about this definition a little bit before we do an example. The first thing is to re-emphasize what I already said. We only define the product of these two matrices A and B when the number of columns of A and the number of rows of B are the same, in this case n. Secondly, we're using the definition which we made on the previous slide actually 2 slides ago, of how to multiply a matrix into a column to make this definition. So we're saying if the columns of B are C1 up to CP, so here this is the matrix B being written column by column, then we get the result by multiplying A into C1, and then A into C2, and then A into CP. Those will be the columns of the matrix product A times B. Okay, we're ready to look at an example then, so let's do that. So we will take A to be the 1 by 2 matrix whose entries are just 1 and 2. So this is a matrix with 1 row and 2 columns. Next, B here is a 2 by 3 matrix. It's got 2 rows and 3 columns. Because the number of columns of A matches the number of rows of B, they're both 2, we can multiply A by B, and the result, the matrix product A times B, will be 1 by 3. So it will be a row vector with 3 columns. And our definition here says that to work out A times B, what we do is multiply A into the first column of B, then we multiply A into the next column of B, then we multiply A into the last column of B. And we use those as the entries of our new matrix. So AB will be obtained by doing these matrix products A times C1, A times C2, A times C3. And if we do that, well, let's do it one column at a time. Here is the first column of B. So to obtain the first part of our answer, we multiply A into the first column of B. So that gives us 1 times 1 plus 2 times 0. And you can see that I've actually made a silly mistake on my slide here. This thing here ought to be a 0. So what the correct answer here is 1 times 1 plus 2 times 0. That is 1. Oops. Let's try and write this properly, shall we? So my first entry here is 1. Okay, next entry then of the product A times B, we have to multiply A into the second column of B. So that second column, highlighted in blue here, is 0, 1. So to figure out the second entry of AB, we do A into the second column of B. So I get 1 times 0 plus 2 times 1. That, if I work it out, is 2. And finally, working out the last entry of A times B, we multiply A into the third column of B, which is 1, 0. So we get 1 times 1 plus 2 times 0. That is 1 again. So A times B is the 1 by 3 row vector, in this case, whose entries are 1, 2, and 1. Let's do another example now, where we have the matrices A and B shown here. So A is the 2 by 2 matrix 1, 2, 3, 4, and B is the 2 by 2 matrix 5, 6, 7, 8. So in this case, A is 2 by 2, B is 2 by 2, and the number of columns of A equals the number of rows of B. They're both 2. So that means we can multiply the two matrices, and the result will be 2 by 2. The number of rows of A, which was 2, and the number of columns from B, which is 2 by 2. So in general, a good way to remember this is to think about multiplying an M by N and an N by P matrix. Well, you can kind of think about the number of the n's in the middle here cancelling, and the result being M by P. In general, if you multiply an M by N and an N by P matrix, then the result, the product matrix, is M by P. So it's a bit like the N in the middle cancelled out. Anyway, let's do this example. So in this example, A times B is obtained by multiplying A into the first column of B, which is this column here, and then using that as the first column as the product matrix. So let's work that out. In order to find the first column of the product AB, we multiply A into the first column of B. So we have to do A times 5, 7 to find the first column of the product AB. So that is 1 times 5 plus 2 times 7 as the first entry right here, and then 3 times 5 plus 4 times 7 as the second entry here. So that will give us the first two entries in our matrix product. So what's that? 1 times 5 is 5, plus 2 times 7 is 14, that's 19. Next we'd have 3 times 5, which is 15, plus 28, which is 43, if my arithmetic is correct. I think it is. Okay, let's now work out the second column of the matrix product AB, and you'll remember that that's obtained by multiplying the matrix A into the second column of B. The second column of B here is 6, 8. So in order to work out the second column of AB, we've just got to do A times the second column of B, which is 6, 8. So let's try and work that out. What's happening here? We have A times 6, 8, so that is 1 times 6 plus 2 times 8. That is the first entry right here. 2 times 8 is 16, plus 6 is 22, so that should be our first entry here. And finally, the next entry is the final entry of A times 6, 8, which is 3 times 6 plus 4 times 8. So that's 18 plus 32. What's that? 42, 50. Okay, so assuming my arithmetic works properly, that is the answer to A times B. So you can see, kind of what's going on here. Well, a good way to think about this is just to think about rows and columns. And you can see what we did here was to find this first entry of the matrix product. That was the first row of A times the first column of B. And the entry here was the first row of A times the second column of B. And here we had the second row of A times the first column of B. And here we had the second row of A times the second column of B. So you get this matrix product by doing rows times columns. And in fact, the ij entry of the matrix AB is obtained by multiplying the ith row of A and the jth column of B, according to the way we defined row times column on our very first definition slide. And that can be a useful way to think about matrix multiplication. So I'll write it down. A times B is equal to Ri times Cj. It's the ij entry whose ij, it's the matrix whose ij entry is Ri times Cj, where Ri is the ith row of A and Cj is the jth column of B. So that comes out of our definition of matrix times matrix from our last slide. But there's also an alternative way to write the matrix multiplication rule, which is more useful in proving properties of matrix multiplication than it is to actually practically compute matrices. So here is that alternative description of the matrix times matrix multiplication we've defined. If you have a matrix A whose ij entry is little a sub ij, and if you have a matrix B whose ij entry is little b sub ij, and if those matrices have the correct sizes so that you can multiply them, so here A will be m by n and B will be n by p, then in that case AB is the m by p matrix whose ij entry is given by this formula here. So the ij entry is the sum from k equals 1 to n of little a ik times little b kj. And if you think a little bit about what this formula is telling you, it's actually just the same formula to do with multiplying rows and columns that I gave you on the last slide. Because think about here what's going on. We're talking about the ij entry of our matrix product AB. And let's just look at the constituents here. So these entries A sub ik, well, what are they? The I is fixed, and the I tells you how far you go down, right? The I is telling you what row of A you're looking at. So these entries are the entries in the ith row of A. On the other hand, if we think about what B's are appearing here, well, here the J is fixed, and the J, the second matrix coordinate, tells you which column you're in. It tells you how far you've gone across in your matrix. So these B, K, J, as K varies from 1 to n, are the entries in the jth column of B. So to find the ij entry in the matrix product AB, you can see that what we're doing is multiplying the entries in the ith row of A with the entries in the jth column of B, just like I said at the end of the last slide. So let me end with an important reminder about the way matrix coordinates work. When we talk about the ij entry of a matrix, the I tells you which row you're in, so it tells you how far you go down, and the j tells you what column you're in, so that tells you how far you go across. That is different to the way in which we normally use coordinates. If you tell somebody the coordinates on a map, like a map of the world or a map of London, the first coordinate tells you how far across you go, and the second coordinate tells you how far up you go. But for matrix coordinates, that's not correct. For matrix coordinates, the first thing, the I, tells you how far down you go, and the second thing, j, tells you how far across you go. It's super important to remember that, and you'll be doing an online exercise just to check that you've got those the right way around. In the meantime, we've now defined matrix multiplication in the most general case, so in our next lecture, we'll look at a bit more about the properties of matrix multiplication.